You might have thought this day would never come, but I have a working version of the Minecraft computer. It's taken, well, I don't know, a long time. It's been very low on my list of priorities, but I did get around to getting a working version of it. I wouldn't call it finished yet. There are a few things that, um, some tweaks that need to be done and some changes in the design that I would like to do, but it is in a working state. It can run programs. So it is a working computer in Minecraft. Is it efficient? No. Is it impressive? Well, no. I mean, depends on how you take that, I guess. But I'm going to give a quick overview of how this works, and then demonstrate that it works. So, if you're noticing command blocks, first of all, a note about the way that this is working. Um, None of the logic of the computer is being done by command blocks. That's because this already was very low on my priorities, and so if I was going to have to do all of the wiring between everything, then I probably was not going to ever get it done. So all that these do is just it will set either air or a redstone block somewhere. So effectively, it's just sending a signal as if it was redstone, but it's not actually doing any of the logic of the computer itself. So all of the actual logic is being handled by redstone. And in terms of design philosophy, this is not meant to be like the most efficient or the most amazing Minecraft computer. I actually intentionally avoided watching any videos of other people's Minecraft computers until I had the design solidified because I wanted to try to design it myself. More for fun. This whole thing is for fun and for, I guess you could say, somewhat academic purposes because I was at the time studying computer architecture. But let's start with the heart of the computer, which is the ALU, or the Arithmetic Logic Unit, I think, if I remember correctly. So this is the addition unit. So here, each layer here, we have the circuitry for addition. There's actually 2 bits being added on each layer of this little tower of circuitry here. So this is 2 bits, and then there's two like result bits coming out from the side, and each layer is 2 bits. So this whole thing is 16 bits. The whole computer is a 16-bit computer. Then you have other just basic like bitwise operations. So you have and, you have or, you have not, you have shift left and shift right, and those are all of the built-in hardware math operations that you can do. Over here, these are the inputs. So a lot of the terminology and everything comes from RISC-V because that's what I learned in college when I started making this. So we have register source 1 and register source 2. Those basically are just 2 things from the CPU's memory that it is going to operate on. So like if you're adding 2 numbers, those are the 2 numbers. And these are technically connected. You can see that like if we take this block here, if we get rid of it, you can see in the distance the blocks disappear from the input over there. And then if we add it back, you can see the blocks showing up over there as input, and the other blocks that are there from that number over there. So that's what I meant by like the wireless circuitry. So that is the ALU. Next, let's go to the whole control unit. Actually, next, let's go to the memory itself, the registers. So I don't know why, but originally I did not make separate instruction versus non-instruction memory, which I decided to stick with that design just until I was done and had a working version, and now I have working version. So I will probably go back and change this because it gets messy when you have instructions and like data stored in the same place. It's doable, but it's kind of weird. But this is the memory for the system. Inside here, each of these spaces here that you see, like here with the copper blocks, that these are the bits of the memory. If they're the presence or absence of a redstone block indicates a 1 or a 0, respectively. And the command blocks coming out from either side and up here control whether it gets sent to register source 1 or register source 2 or to the instruction input, or to the control unit. So basically, those are the outputs. That's my wireless wiring. There is a special one. There's a special register here, register 0. There's some extra bonus stuff going on down here, which basically the signals from, or the data stored in register 0 gets displayed here. So that's kind of like if you want to display a number like your answer, just put it in register 0 and boom, there it is. So our little console, we'll come back to the console a bit later. But that's how you can display numbers. This is our control unit over here. So we have opcodes. So if you're not familiar with how computer architecture works, basically all of the instructions are just numbers. So part of the number, which it's in binary, part of the number, in this case the 4 farthest right digits, are the codes that determine what kind of command it is. And right here we have, this is the command, when it comes in. So these 4 right here, depending on what combination is here, it will, well actually these will just copy the opcode to each one of these, and each one of these will only respond if it has the correct opcode. So you can see here, if this is 0, then it will send the signal here. If it's not 0, if any one of these has something here, it will not send the signal through to that. So that's how each one of these works, basically. It's just like a a gate that accepts that number and only that number. You'll notice these bone blocks that are randomly sitting here. You'll see this throughout a lot of the computer. And basically what this does is it controls the timing of it so that it gives time for the redstone to work. So once time has been given for the redstone basically to get all of the signals organized for the signal to run through all of the logic that it has, then the bone blocks will get replaced with redstone so that the signal will come through here. And we'll see that controlled by the clock later on. These just copy the inputs over to their respective places as needed, such as the registers, such as other control stuff. So some of these send new clock counters, new PC counters to the clock. We'll get to that. And if we go over here, and those are all what gets sent gets controlled again based off of the opcodes. So there's a lot of stuff where you could call them control wires, I guess, of whether the bone blocks are there or not. Basically is whether or not this thing gets used. And there's one more thing here too. This takes the register destination, which is where we're going to save a value, if we're going to save a value, and it takes this, I forget the name of it, multiplexer, I think, or splitter or something. It takes this thing that takes the signal and it divides it up into all of the 15 possible places it can get saved and sends it there. And this controls which direction through this path, through this mess of redstone, the signal actually goes through in order to get saved. So I don't know if that made any sense or not, but this is a very high level overview of how all of this works. I do have some other videos going into more detail. Over here we have the clock itself and the counter for what instruction we're on. So This will control what instruction gets loaded up next. You'll notice this is basically just the addition unit from over there, except that it's much smaller because we only have at most a 4-digit address. So this just basically adds 1 each time so that we count through and go through all of the instructions. There are places where it can there are commands that can substitute in a different value for this so that it will jump to a different place. But if that doesn't happen, it will default to just adding 1 each time. This thing over here controls loading the instructions. So kind of like that, but on a much smaller scale. Whichever instruction is supposed to be loaded, it will it will control which path the signal follows, and then whichever path it follows, that will load that specific instruction from memory. And this is actually the simplest but the most important part. This is the clock. So it starts somewhere along here. I think it starts here. I actually made this a couple months ago and then forgot to make a video about it. Somewhere along here it starts, and it goes around in a circle. And what it does is it just controls the flow of when things happen. So like, here's where we set the new PC value, and here's where we increment the PC, and here's where we load the instruction. And then all of these delays that are here are just to give time for the signal to run through all of the circuitry that it needs to run through. So the thing that takes the longest, this whole long section here, is for the ALU. So it takes a lot of time to make sure that the Redstone signal has gone all the way through everywhere that it needs to, so that we know that we have the correct output. And that's what all of these delays are for. So this is a very slow and very inefficient system, but it does work. Then we get back around to the beginning again. We check if we saved the value from that, and the whole process starts over again. And there is a halt command, and halt just adds these redstone blocks here that stop the signal at wherever it's at. That way we don't keep running through all the instructions. So now let's try running it. Actually, one last thing I forgot to say is the console here. So I said this displays whatever's in register 0. We also have an error bit that can be set in the code. That way, if we want to check that it's dividing by 0 or something, we can like halt and turn on the error bit so that we know there was an error. This just shows that the program's running. That way we can know what's happening, whether it's stuck in a loop or not. This is the program counter so that we can see what's happening and check what instruction we're on. And here we have start and stop, the very important controls. This is our programming console. The lights are not hooked up yet, which will be annoying here in a bit. But the way that this works is here is the place in memory, the address. So if we want to save something in place 1, we would just do that. These are in binary, so 0001. And then if we want to store, let's say, the number 1 in location 1, we'll just click that for the number 1, and then we do set. This is why the lights being here will be much more helpful when it's a big number and you're trying to keep track of what you're entering in. But that's how you enter stuff in. So if we go to position 1 here, we'll see that there is in fact the number 1 saved here, just 1 and all zeros. So as a quick little demonstration, you can do something really simple. So let's say we want to add together, we'll have 2 numbers and we'll add them together. So I forgot to mention this, but the program counter will start at instruction 1. So that way we don't have whatever's in like the storage here, or whatever's in the display value, won't run. These are the issues that happen because we're using shared memory for instruction and data. That's something that I do intend to change in the future. So that being the case, that means we have to start with the instructions first. So if we want to, let's say, add, we'll add 5 and we'll add 6, so we should get 11. Let's store 5 in, we'll just put it in, why not? Let's put it in instruction 5, or in, like, position 5. So if we have 5, and we'll do set. And then we can clear this here, and we'll put 6 in 6, let's say, just for fun. Now, for the actual instructions, we'll do, so the opcode for AND, or for, not AND, for add is just 0, so we won't add anything here. This part is the place that it will be stored to, so we'll also leave that as 0, because we want it to be stored where, or we want to store it where the display is. This part is the first number we want to add, which was 5. And then this is the second number, which is 6. And these are not the numbers, these are the addresses, but it just happens to be that the number is the same as the address in this specific case. And we'll store this to position 1, so it's the first thing that happens. And we'll do set. And then we have to do one last thing. We want to make sure that it halts, so at position 2, we'll add halt, which is just 1111 as the command, and we'll do set. So everything should be ready. Let's go ahead and clear the 0 as well. There we go. So everything should be ready. I'll go ahead and hit start, and the program should run, and we should get 5 plus 6, which should be 11 right here. And it's going to take a long time. Oh look, the program's running, and it's running instruction number 1. And we only have 2 instructions, add and halt. So we get 11 saved, it goes to instruction 2, and it halted. The program stopped running. It ran exactly the way it's supposed to. And you can see how terribly slow it is. So let's do something longer. So often people use the Fibonacci sequence as a simple program because it involves a loop, and so it runs a little longer, and it's kind of fun to watch because you get to see the numbers get bigger. So I will not enter in all the numbers live in real time because it will take a very long time to enter in all those instructions. But I will do that really fast, and then I will show it run. And there we go. That should be the last one. So Minecraft added a nice feature during the time that I was working on this computer, and that is the ability to change the tick rate in vanilla Minecraft, which part of my whole project with this has been to do it in vanilla Minecraft without using any other tools or mods or anything. And that is something that is going to be very helpful for this, because we can actually watch it in a more reasonable amount of time. Because if we do it, well, we'll go ahead and start it. As you can see right now, the program runs very slowly. Alright, let's try that again. It turns out I mistyped one of the codes. So let's try it again. Here we go. And let's see if we can get it done in one Minecraft day, or if it will take longer. We can see it's working. The ding is every time something gets saved to memory. But the it's just that we're not seeing everything because it's saving stuff to other places in memory that aren't on the display itself. There we have it. We have a working Minecraft computer.